Hi and hello everyone. What we have been seeing was this Poisson process. Recall that the definition that we have seen in the previous lecture, that this is a counting process, right? This is a counting process and it is a homogeneous Poisson process with rate lambda. If it satisfies these three conditions, that it starts at 0, it has independent increments, and the number of events in any interval of length t has a Poisson distribution with parameter lambda t, and because this parameter is also independent of time. So, this means that this process has stationary increments. This also we have seen, and the Poisson process probably restarts itself at any point of time. And we also gave an alternative definition where the third condition in the previous definition we have replaced with this orderliness property by defining what do we mean, what is the probability that one event happens in a small interval of length delta t, and we use this to obtain this difference equations, and by showing that we showed that this process is n of t is having a Poisson distribution with parameter lambda t or with mean lambda t, and we said that the understanding of how to derive this differential difference equations as we exhibited in this argument is what you need to keep in mind, because this is what we are going to use later as well. Okay. Now, let us look at the some more properties of this Poisson process. Okay. But first, let us look at the connection between this Poisson process and the exponential distribution that we have seen earlier, right. So, what is that? It says the following: if n of t is a Poisson process with rate lambda, then the time between successive events, which is we might call that as inter-event time. The event could be arrival or service completion or whatever be the event. So, that inter-event times, they are independent and exponentially distributed with parameter lambda, means that the inter-event times, they are all exponential with parameter lambda is what we have here. So, basically what this says, let us draw the timeline here. So, there are some time points here. Okay. There are some time points here. Now, if this is duration, if I want to call this as T1, T2, this is T3 and this is T4 and so on, that means that this is this interval, T3 is this interval, T4 is this interval and so on, right. Now, let us denote this T1, T2 be the inter-event times, right. So, of course, what happens is here the state of the process is 0. So, this is over time 0 as well, right. That is what is the Poisson process is, and if it is has rate lambda, then what happens is what then we are going to see. So, if T1, T2, if you denote the inter-event times, meaning that at this point of time the first event happened, and here second event, third event, fourth event, you can correlate this with arrival to a queuing system, something arrival happens, right. In general, it is an event. So, this could be the time, and this is the inter-event time. So, starting at 0, this is where the first event happens, then from here it took up to this much time for the second event to happen. This is the time of the third event, this is the time of the fourth event and so on. So, we have now you can see that suppose if I want that probability that T1 is greater than particular t, okay, I pick a time t and I see that the first event happens after time t. What would that mean? That would mean that there is no event happens up to time t. That means n of t remains as 0, starting at n of 0 equal to 0, n of t is equal to 0, right, at time t. So, this event, that the first event happens after time t, is the same as there has been no event up to time t, right. So, this one we already know what is the distribution of this n t, and from there we can immediately write it down that this is quantity is e to the power minus lambda t. So, this is the complementary CCDF or the survival function of this particular random variable t1, which is e to the power minus lambda t. So, probability of t1 less than or equal to t is 1 minus of e to the power minus lambda t, which is nothing but the distribution function of an exponential random variable with parameter lambda, and hence my t1 is exponential with parameter lambda, right. So, that is easier, t1 is very easy to see here. Okay. Now, let us look at t2, right. So, let us look at this t2. What we have for any s greater than 0 and t greater than 0, given that my t1 is s. So, that means what? This time point I am calling this as s, right. So, this time point is s here. Okay. So, given the fact that the first event happened at time t, what is the probability that the second event will occur t time units from this s, right. That means the inter event time is at least t. So, that means what? This means that there is no events in s to s plus t, given that t1 is s, right, no events in this, right. Again, by the independent increment property, that no matter what had happened in up to time s, anything that is happening in the interval s to s plus t is independent of the past. So, that means no event in s to s plus t. Again, because of the stationary increment property, that this s has no relevance. So, it will be equivalent to no events in 0 to t, right. That means that in an interval of length t, there is no events happening. The n of t is equal to 0, right. So, this is what it is, which is equal to e to the power minus lambda t, right. So, this is again, it will be probabilistically this is equivalent to this, that is what we are saying, right. So, no events in s to s plus t. First, independent increment property tells you that this probability is same as probability of this, and again stationary increment property will give you this probability is saying this same as no event in 0 to t. So, that means this is what it is, and that means this is equal to t. So, as this are not influenced by what happens in this. So, t2 is independent of t1 and has again exponential with parameter lambda. Similarly, we can establish that t3 is independent of t1 and t2 with the same distribution and so on. So, this is the sketch or how you can see that this is actually the happening, right. So, here what we are saying is the following: if nt is a Poisson process with rate lambda, then the time between the occurrence of events is IID exponential with parameter lambda. Now, what about the converse? The converse also holds, meaning that if there are certain events, there is an event, right, and for which the inter event times are all exponential IID with parameter lambda, then the events occurring according to a Poisson process. The number of events that is happening is according to a Poisson process with rate lambda, and hence this gives a characterization of a Poisson process as well. So, this is that if the inter event times are exponential, then the number of events will follow a Poisson process, right. If there is a Poisson process, then the inter event times are IID exponential. So, this is a characterization, and this connection, this Poisson exponential connection or Poisson exponential model, and sometimes this is also referred to as Poisson exponential model. So, it means that in a Poisson process, it is always the case the inter event times are IID exponential. If the inter event times are IID exponential, then the number of events happening is according to a Poisson process with rate lambda. Okay. So, this is the connection is also important in many ways, and one way is that in simulation of a Poisson process, obviously like you may have to simulate in some situations a process. Now, how do you simulate that? You will generate an exponential random variable, and that would give you the time for the next event of a Poisson process, right. So, that is how you will use it, okay. And like how you can simulate an exponential random variable, because that is we are not touching, but of course, that is very much closely related to the topics that we might use, and when you are actually applying this whole of queuing theory to some realistic situations. Okay. Now, this Sn, right. So, this is, if you denote this the time of nth event by Sn. So, basically S1 will be equal to T1, S2 will be T1 plus T2, S3 will be T1 plus T2 plus T3 and so on. Sn will be the sum of the T's from 1 to n, right, the inter event if you sum. So, that is the time for the nth event to happen, and the sum of exponential is gamma. So, the time of nth event would follow now a gamma distribution, or this is you can also sometimes refer to as the waiting time distribution, waiting time for some particular number of events to happen. So, waiting time for 10 arrivals, waiting time for 20 arrivals, 20 failures in some production system and so on, right. So, these are all would be then gamma distribution is what then you would see. Because of exponential, the sum of exponential, IID exponential is gamma. So, that will give you the waiting time distribution in a Poisson process follows a gamma distribution. Okay. So, now let us look at a simple example and see like what kind of questions that can arise in such situations and how they can be answered through a Poisson process type of model. So, here basically we are looking at the Poisson process model. Okay. Now, consider a car insurance claims reported to the insurer. Assume on an average the rate of occurrence of claims is 10 per day, means per day there are 10 claims comes on an average. This is based on the past record. Now, also assume that this rate is constant throughout the year and at different times of the day. So, this is irrespective of the time of the day, irrespective of the day of the year. For the whole year, it is going to be 10 per day is what is happening. Further assume that in a sufficiently short interval of time, there can be at most one claim, right. So, it means that there is no group claims, that is what you are assuming, that at any point of time whenever the claim occurs one at a time, right. That is what pretty much it would mean. Okay. Then the question is, what is the probability that there are less than 2 claims reported on a given day? Okay. What is the probability that on a particular in a given day, what is the probability that there will be less than 2 claims? Similarly, given you are standing at some point of time and you are looking at when will be the next claim will happen. So, the probability that until the time until the next reported claim is less than 2 hours. So, what is the probability that from now the next 2 hours, like I am going to get one claim, what is the probability for that, right. Of course, there could be many questions that you can ask with respect to this. This is just a simple scenario. Now, based upon our assumption starting from here up to this, we can see that this can be modeled through a Poisson process. Okay. And the number of arrivals of car insurance claims to the insurer in a time interval of length t is a Poisson process with rate lambda, which is now 10 per day. So, lambda is 10 per day. So, now what is the probability? First question is that the probability that there are less than 2 claims reported on a given day. So, the day could be any day, right. So, in that particular day, which could be like the t plus 1th day, you may be standing at any time t, right. So, what you are looking for is n of t plus 1 minus n of t is less than 2, right, less than 2 claims. It means either 0 claim or there is at most 1 claim, that is what you are looking at it. Okay. Less than 2 claims is not less than or equal to 2 claims. So, it is less than 2, it is strictly less than 2. So, this by the stationary increment property, this would be same as n of 1 minus n of 0 less than 2, and n of 0 is 0. So, n of 1 less than 2, that is what you are getting it here. So, that means this is either n of 1 equal to 0 or n of 1 equal to 1. From the distribution of this n1, you can immediately write down what are these probabilities. This will be this quantity, that is 11 e to the power minus 10, which is approximately equal to this. So, you have 0.0005 as the probability of less than 2 climbs in a day, means either 0 climb or there is 1 climb with this probability. That is what you are getting it. Similarly, the next question, what is the probability that the time until the next reported climb is less than 2 hours, right. So, what you are having here is the required probability that the time until the next reported less than 2 hours. 2 hours now, since things are done in day per day business. So, you have to represent this as number of days. So, it is 2 by 24 days is effectively probability of t less than 2 by 24, where t is the inter-arrival time and that follows an exponential distribution with parameter lambda, which is already given to you. Now, again here what you are, so the past, when did the last event happen has no bearing on the future, that part you are remembering, because that is independent increment property, and also at what time you are looking at it is also not relevant because of stationary increment property, right. So, all these things will give you that the required probability is simply probability of t less than 2 by 24, which if you compute, which is exactly equal to this, which is equal to this, which is 0.56. So, there is more than 50% chance that in the next 2 hours you are going to get 1 climb, right. So, it is 50% chance is there, that is what it says here. So, like this different situations, of course, you can look at the different books when you are dealing with Poisson process for various kind of examples, models. Basically, the underlying assumption should be such that the Poisson model can fit in there. So, that is what is important. Okay. Once you are ensure that the underlying assumption would fit, when things are going to happen in a random fashion, then you can always take a Poisson process model as a first cut model. Okay, so next what we are looking at is basically some more properties of this Poisson process. The first one is what we call Poisson thinning process or splitting or decomposition process. What is that? Now, consider a Poisson process n of t that has a rate lambda. Suppose that each event is classified as a type 1 event with probability p or a type 2 event with probability 1 minus p, independently of all other things that is happening in the scenario. Okay. Now, if I call n1 of t as the number of type 1 events and n2 of t as the number of type 2 events occurring in 0 to t, but note that n of t is n1t plus n2t, right. So, each event has a probability of p of being of type 1 or 1 minus p of probability of type 2. Okay. So, you can assume a production unit where the units are coming out one by one, and you see that each unit, so the production is happening, of course the production units are coming out in a Poisson fashion, that is what you are assuming. Then each unit can be either defective or not defective, defective with probability p and not defective with 1 minus p. You can associate some such scenarios to make sense of what this kind of things happens here. The only thing is that it happens randomly, and the arrivals, the number of units being produced follows a Poisson process model. Whether it is true or not, of course, it is leave it to the underlying situation that you are trying to model, but if so, then this is what the scenario would represent. Then what is the claim? The claim is that n1 of t is a Poisson process with rate lambda p, and n2 of t is a Poisson process with rate lambda times 1 minus p, and these two processes are independent. Okay. You can look for the proof elsewhere, it is not very complex one, but you can just give you a sketch so that you understand the use of the total probability law that we repeatedly said, how much you have, you apply everywhere, and this is a situation where. So, basically let us take this n1 of t, we want to show that this is a Poisson process, which means that probability of n1 of t equal to n should follow a Poisson distribution with parameter lambda p t. That is what you want to see. Let us see how this can be done. So, probability of n1 of t equal to n, right, this is what you want to compute. Now, this can happen, right. So, the type 1 events are n, that means the total number of events that would have happened is at least n. So, suppose if you assume that it is n plus r is the total number of events that has happened. So, n of t equal to n plus r, where r is from 0 to infinity. Out of this n plus r, given that n of t is equal to n plus r, my n1 of t is n, is what I wanted, right. So, this is what is the conditional probability or total probability law that you are using it here. You are conditioning on certain events whose union is omega, and that is what this you are summing it up here. Okay. So, this is what is the quantity that you are writing it down, right. Now, what is this quantity? This quantity is simply this, right, n plus r events happening in a Poisson process with rate lambda is simply given by this expression of Poisson probability evaluated at n plus r for the parameter lambda t, right. Now, here n plus r is total number of events, and out of this n should be of type 1, since so this can happen according to a binomial distribution, right. That is what it is. So, n plus r c n p to the power n 1 minus p to the power r, right. Out of this n plus r, any n of them can be the type 1 events, and each of these occurs with probability p to the power n and 1 minus p to the power r. So, total is n plus r, right. So, now you just have to do manual calculation. So, this n plus r c n you can write as n plus r factorial by n factorial times r factorial. So, this n plus r factorial gets cancelled, leaving out with only this e to the power minus lambda t, I take it out. Then I can write this as n plus r, this lambda t, I can club with 1 with p, 1 with n minus r. So, you will get this expression. Now, this sum is with respect to r. So, this n to the power n and n factorial I can take it out, and the remaining one if I sum it up I will get this quantity. Now, club this e to the power minus lambda t with this, you will get e to the power minus lambda p t. So, this is the expression that you are going to get, and which shows that n1 t is a Poisson process with rate lambda p, or n1 t is a Poisson distributed random variable for a fixed t is lambda with parameter lambda p t, right. So, similarly you can do n2 of t, and then you can show that these are independent and so on, right. This is what it actually means. So, basically what we have here, if I depict pictorially, that there is a Poisson process with parameter lambda. Now, I have two branches here. So, with probability p and with probability 1 minus p. So, this will be Poisson process with parameter lambda p, this will be a Poisson process with parameter 1 minus p. Only thing that you need to keep in mind here is that the arrival here goes either this way or this way in a random fashion. Every arrival has a probability of p of going to this route or taking this route with 1 minus p. If this is done deterministically, then this is not going to be a Poisson process, this is not going to be a Poisson process. Say for example, when you are entering into some queue, so the odd one is being sent to one queue, the even one sent to the other queue. There are two queues and then you are being sent to this. Okay. The first customer is sent to the number 1 queue, second customer number 2, third customer number 1 queue, fourth customer number 2 queue, and so on. If it goes in this fashion, then the assignment of a particular customer would depend on the previous customer's assignment, right. So, this is not independent. So, this is not happening, the assignment to a particular queue is not happening in an independent fashion, and hence the arrival to the individual queues, if I look at it, it is not going to be a Poisson process. Whereas, in this particular case, when each of these arrival has this kind of behavior, then so where this is more relevant, like you are going to see later that especially in networks where some arrival happens and then with certain probability this will take this route, with certain probability this route kind of business, right. So, in such situations, if I want to look at what is the arrival process at the individual nodes, then it will be a Poisson process by this property. That is where this will be more useful if I want to look at the decomposition or thinning process or splitting of Poisson process. Okay. This is one important property. The other important property is superposition. This is just the reverse of what might happen, what has happened to the previous scenario. Here what you have n1 of t, n2 of t, they are two independent Poisson processes with rate lambda 1, lambda 2 respectively. Then their sum, which if you call this as n of t, is a Poisson process with rate lambda 1 plus lambda 2 is what you want to show. So, again what you have here is that you have a Poisson process here, Poisson process with rate lambda 1, this is Poisson process with rate lambda 2. So, this will be a Poisson process with lambda 1 plus lambda 2 is what this will be the case. So, what you have here, the assumptions, these are individually Poisson process and they are independent. The independence is also important for this to hold true. Okay. Now, how do you see? Again you know that the probability generating function of a Poisson random variable is of this form, e to the power lambda times z minus 1, and here since it is a Poisson process, the parameter is lambda I times t. So, this is would be the PGF of a Poisson process n I of t, where lambda 1, lambda 2 for 1 and 2. Now, the PGF of n of t, which is the sum of this, is basically this quantity, which is z to the power n1 t plus n2 t, and because n1 and n2 are independent, now that is given by the product of this individual PGFs. Now, if I substitute these two, what is the case here, then you will get here. So, this is the PGF of a Poisson process with parameter lambda 1 plus lambda 2, right. So, that is what is you are showing it here. So, this is the reverse, again superposition from different streams the arrivals are coming, and if they are all independent, and the combined arrival process now would be a Poisson process as well. So, that is what you are looking at here in this particular scenario that you are looking at here. Okay. So, this is a superposition property. One other property which is also important in our context, and to say that why this particular process is called a completely random process is because of this fact which we are looking at now. So, what is that where we have? We have as usual Poisson process with rate lambda. Now, you are given that by time capital T there are n events have happened, and the events happen at the time points say S1, S2 and so on Sn. Okay. Now, if I look at what is the joint distribution of these event times, right, when these n events have happened, okay, they will have the same distribution as the order statistics corresponding to n independent uniform random variables on 0 to t. Okay. So, this result is you can easily show if you recall this fact from the probability theory, which talks about the joint distribution of order statistics. What do we mean by that? So, you have n random variables which are IID random variables with their PDF small f, okay, and we denote x suffix bracket I to be the ith smallest of these random variables. Then this n elements, right, x order 1, order 2 and so on order n, this is called as order statistics, right. This is what we do it in probability. So, for example, this x1 is nothing but the minimum of x1, x2, x3 and so on xn, x2 is the second minimum, and x3 is the third minimum and so on, and xn is the maximum of all these n random variables, right. So, x1 and xn you can handle, the other ones you need certain theory to arrive at their joint PDF, and the joint PDF is given by this expression. Okay, this is we are directly taking it from probability theory idea that the joint PDF is given by this. Now, the marginal PDF of the ith one is given by this, where capital F is the CDF of this random variables, they are all IID. So, any one of them is what then we mean this capital F. So, this is what the quantity here. Now, if I use this one, right, and if I take F to be uniform in 0 to t, then what I would get is this, right, and that is what you will obtain it as the joint distribution of the order statistics corresponding to n independent uniform random variables on 0 to t. You will obtain at this. So, this Poisson process, as we said, is sometimes said to be a completely random process or a purely random process. This, the word or the justification for that comes from the fact that the events are happening in a uniform fashion, in a way that uniformly distributed in time. Say for example, you know that at particular time t, one event has happened. Now, given the fact that say at particular time t naught, one event has happened, what is the probability that it would have happened at any point in the interval 0 to t naught, if you look at it, and that is uniformly distributed between 0 and t naught, meaning that it could have happened at any point of time starting from 0 up to t naught at any point of time. It has an equal probability of occurring, right. So, that is the uniform nature of, that is what it could happen in a random fashion, right. So, what this uniform property means is that given that n events occurred in 0 to t, the unordered event times are independent uniformly distributed, right, meaning that if I have say time 0 here and time t here, okay. So, the events could have happened somewhere here or somewhere here or somewhere here, right. It could happen in a completely uniform fashion. So, any events if you pick, they could have occurred in any of these time points uniformly between 0 and t, right, or in an equivalently if you have to specify like what we just shown, the ordered event times follow the order statistics of n independent uniformly random variables, right. That is what we simply said in the previous slide, that this is what we mean, that the orderly events, right. So, for example, an event could suppose 0 to t 1 is what the timeline that you are looking at it, and suppose one event happened at point 2, other event point 8, the third event at point 6, right. Now, this is not orderly manner. So, any event can happen between 0 and 1 at any point of time, but now if I take its orderly manner as first point 2, then the third event which happened as point 6, which is x 2 now, and point 8 is x 3 now. So, this one will be the order distributed as per this quantity, that is what it would mean, right. So, that is what it means. So, it is completely independent and uniformly it can happen at any time between 0 and t, any of these n events. That is what this property would mean, and that is the why Poisson process is called as purely random process or completely random process. So, it might so happen that by time t n events happen and all n events could have happened here, all n events could have happened here, all n events could have been happened at equally distributed intervals, anything can happen. So, that is what this would mean in this case. Okay. So, one important consequence of this uniform property of the Poisson process is that the outcomes of random observations of a stochastic process have the same probabilities as if the scans were taken at a Poisson selected points. Okay. So, you have a timeline, right. Now, you look at this process at some random point of time, and also you look at the process at a Poisson selected points, which means that wherever an event happened according to some Poisson process, so you are looking at, you are marking that points in the timeline and you are looking at the process only at that time points, how the process will look like, and you are looking at an arbitrary selected time points of the process. Now, how will these the views of the process will be for you when you are looking at these two sets of points, right. So, this uniform property of Poisson process makes that the observations at whichever time point that you are looking at is irrelevant, they have the same property, right. So, they have the same probabilities as if the scans were taken at a Poisson selected points. For us, this is an important property which is called as PASTA, meaning Poisson arrivals C time averages, right, where typically in our case this xt will be number in the queue. So, the number in the queue is what is the process that you are looking at it. Now, the question is whether the number in the queue you are looking at any random point of time or at the arrival instance. Now, the arrival instance when you are looking at the number in the queue or any random point you pick and then you are looking at the number in the queue. Now, how will these two probabilities will differ? In general, they need not be the same, but for Poisson arrivals, they will be the same, right. So, that is what is called as Pasta property, which is very relevant because at what time you are looking at the process is also important in certain contexts. So, this property gives you that it is irrelevant as far as Poisson arrivals concerned, because Poisson arrivals see time averages. Random point of time when you mean it is the time averages over a long period of time, what is the number that you are looking at, that is what will give you the time averages. Now, Poisson arrivals will see time averages is what this property is. Of course, this is an important property with respect to Poisson arrival case, and that is because of the consequence of this uniform property of this Poisson process. Okay. So far what we have seen is this Poisson process ideas and its certain properties. Of course, there may be many more properties, but the properties that are most relevant for us we have listed out, and their implications and consequences also we have listed out. There are many generalizations of this Poisson process. As we said, this is a first cut approximation. A very elementary level approximation process is what is done by the Poisson process model. There could be many generalizations. We will be at least one generalization is very relevant for us is what we call as the compound Poisson process, right. Compound Poisson process. What does that mean? We are defining it in this manner. So, NT, you take a Poisson process with parameter lambda, okay, and you pick an IID sequence of strictly positive integer valued random variables, and that is independent of this n of t, and you call that sequence as yi. Then the stochastic process MT, where MT you define to be this quantity. What is that quantity? Sum of yi's for I ranging from 1 to n of t, and this is said to be a compound Poisson process. Okay. This is said to be a compound Poisson process. Now, when this yi's are IID sequence strictly positive integer valued random variables, means this takes values 1, 2, 3, 4 and so on, that is what you are looking at it. Now, if with probability 1, if they all take value 1, which means probability of yi equal to 1 is equal to 1 is what the condition, then this would simply be equal to n of t, right. So, you get back your original Poisson process. If not, so this yi is if need not be equal to 1 with probability 1, so it can take any values 1, 2, 3 and so on. Then this, so each yi will be 1 or something more than 1, but it is an integer, positive integer, right. So, their sum is what then would be MT, and this is what is called a compound Poisson process. Basically, what you have scenario is that you have a Poisson process where the events occur according to a Poisson process, but the number of events that occur at a particular event selected time is not just 1, it could be more than 1. If it is 1, it becomes simple Poisson process. If it is 1 more than 1, then it becomes a compound Poisson process in general, right. So, meaning that the events occur in some sense in groups or in clusters. That is why this is also called as a cluster Poisson process. Clustered Poisson process means the events occur in clusters, but the inter-event times are all exponentially distributed, but the event occurs in clusters, in groups, in batches. That is what it would mean. So, that batch size is what effectively this yi, right. If the batch size is equal to 1, then it becomes a simple Poisson process. If it is for a general one, then it becomes a compound Poisson process. Okay. Now, if NT is a Poisson process with rate lambda, then expectation of MT is lambda t times e to the power, expectation of y1, and variance is this, which we have already obtained it in the earlier case when we are dealing with random sum. Recall random sum quantities that we have dealt with. So, that random something is one such instance is occurring here is what then you are seeing it here. So, examples could be like suppose that buses arrive at a sporting event in accordance with the Poisson process, and suppose that the number of fans in each bus, they are independent and distributed, then this total number of fans who arrive by time t would be a Poisson process. This is the total number of fans who are the spectators who arrive by time t. Okay. Now, customers leave a supermarket in accordance with the Poisson process, they leave. Okay. If yi is the amount spent by the ith customer, and we are assuming that this yi is as per this constraints that we have here, then mt is a compound Poisson process where mt denote the amount of money spent up to time t. Okay. Many such scenarios in queuing, mainly we were looking at bulk arrivals, bulk service, things where you will need this compound Poisson process. You can always think about bulk arrival systems as having compound Poisson process arrivals. Okay. The other generalization which we may not deal with in this course, but it is very relevant from a practical point of view is and hence I will just hint it, it is not, will not do much on this, is what is called a non-homogeneous or non-stationary or inhomogeneous Poisson process, right. We said that lambda t parameter lambda that we have got for a Poisson process is constant with respect to time, meaning that the rate of arrivals happens at a constant time, at a constant rate at all time points, right. We just set an example of an insurance claim comes, right. Whether it is daytime or night time, or if you are considering only day as one time unit, or whatever is the case, right. You are assuming that throughout the day it occurs at the same rate and so on. But in many situations this may not be the case. For example, if you take a hospital scenario, right, then even insurance claims, suppose for example, if you are looking at say agricultural claims for example, whenever there is it's in certain seasons, like only you will get more number of claims, in certain seasons you will get less number of claims. So, obviously this will be time dependent. Similarly, in the case of hospital, right. So, the arrival rate at morning and lunch time and evening and late night, things are not going to be the same rate. Same thing in a traffic junction, if you are looking at the arrival of vehicles, like it will not be the constant rate of arrival throughout the day, right. Then one can easily do business with that, but that is not going to be the case, obviously time dependent ones, and right. So, that means this lambda is not a constant, but it is a function of time. Okay. So, this is more realistic than a simple Poisson process, a non-homogeneous Poisson process. So, it has the exact same property everything except that the parameter rate is lambda of t. So, it has independent increment property, it starts at 0, it has this orderliness property, but what it has lost is the stationary increment property. Now, in this process the increments are not stationary in time, like because it is obviously the time dependent ones, that is what it is. Whereas in compound, in the previous generalization that we have seen, which is basically this compound Poisson process, you have starting at 0 independent increment property, stationary increment property, but it has lost the orderliness property because there could be more than one arrival can happen. But here we are retaining this orderliness property, but we lost the stationary increment property. Okay. So, that is what happened here. Again, this is with mean event rate lambda t, the number of events in an interval of length s to t is given by this, where mt is 0 to t. So, mt minus ms means is effectively s to t times lambda u du is what will be the mean in a number of events in the time interval s to t, because we have to now depend on which interval you are looking at, because these things are not stationary in time. So, this mt is sometimes called the mean value function, it represents the cumulative things that you have here. So, this is a simple example where lambda t takes value 2 values 5 and 3 depending upon which interval of time this is here, then the number of observed interval in a particular time period. So, this we have to find out this which 2 different values. So, this is what is basically this mean Now, once you have this mean, then you can obtain through the Poisson distribution this particular quantities that we have. So, this is a simple example that we have. Okay. Of course, non-homogeneous in our course we are not going to deal with it, but better thing is you are aware about such a situation. It can be handled in a quite a bit easier way using the simple properties that we already have for Poisson process. You can do. You remember that stationarity property, stationary increment property is not there. That is what you have to keep in mind when you are dealing with non-homogeneous thing. Okay, before we wind up, we just note a few points. This Poisson process, we said that we are looking at this as a special case of continuous time Markov chain. Before we move to CTMC, we are looking at this Poisson process. Okay, it is a special case of continuous time Markov chains, but it is also a special case of a larger class of processes which are known as renewal processes. Okay. So, this is basically a renewal process arises from a sequence of non-negative IID random variables denoting time between successive events. The inter-event times are still IID and we are looking at the number of events happening just like Poisson process. The only difference there is that instead of exponential distribution, we could have a general non-negative IID random variable. Then the process will become a renewal process. The quantities of interest is again number of renewals happens by time t, just like number of events happen in a Poisson process by time t, which we have found out to be a Poisson distribution. Okay, so that you can get the quantities immediately. But here it is not, the inter-event times are not following an IID exponential, but it is IID random variable, but it follows a general distribution which is has support on the non-negative real numbers as the quantities as a support for that random variable. That is what you call it renewal process. Now, what happens is that at the points of the events, like the process will behave like a Markov chain and all, but otherwise in general it will be a renewal process. It is what. So, now only thing is that memoryless property and everything will be lost. So, you need to keep track of the when the last event has happened, okay, because it is not exponential anymore in inter-event time. So, the same problem that you are doing with Poisson process, if you remove the exponential and if you have to do this, then you will need some more ideas to tackle the problems, right. That is what it will become. We will see when we start the semi-Markovian queues, we will see a little bit about this renewal process before we start the semi-Markovian queues. Okay, right. That is what. So, but many of the properties of this Poisson process also hold true for renewal context, as we will see later. So, with this we will end this our discussion on Poisson process. With these ideas in mind, a simplest case of a continuous time Markov chain, we will now do the continuous time Markov chain ideas. We will see in the next lecture. Okay, thank you. Bye.